All right, I'm sharing my screen. I'm not on mute. It's almost like I know what I'm doing. Okay. I haven't posted this for you guys, but then I realized, you know what? I think maybe, just maybe, you might like it. Because last week, where is it? Open in Notability. I want to put it in here, I think. Open Note. Because last week, we kind of wrapped up inference. I'll zoom in on it in a little bit, but let's just get some lines on here. Yeah.
Mine was a 98% confidence interval, so isn't it 0.02 times your
I'll go in and
0.02 times my DF, which is 21.
Oh, the subscript DF is just to indicate that it needs that degrees of freedom. Let's see here.
Is that not how you calculate the critical value though? You do the T equal bracket, you have the 0.02 times the.
Let's do equals T inverse, right?
Yes, ma'am.
All right. Oops. T inverse, and then you want the area to the left. So for a 98,
0.02.
Divided by 2, because you split it evenly in the tails.
That's what I was missing then.
There you go.
Yep, thank you. Help me already. I use a late pass, so I'll be able to.
There you go. Yeah, and then whatever the degrees of freedom, let's say 20. Just for completeness sake.
Gotcha.
Yeah.
Dividing by 2 part.
It should be, for a 98, it should be kind of close-ish to 3, right? And so just make sure that you get, yeah. Hey, how come it's positive?
I was gonna say I have a negative.
It should be. It should be negative. And if you want the positive, so the reason it should be negative is because it looks like this, and we forced this area to be 0.01, which also forces, of course, this area to be 0.01 and this to be 0.98. And then this should be the negative version. But I don't know why it went to a positive. That's kind of weird.
So if it goes to a positive, you can just throw a negative in front of it.
Yeah, because you have the plus minus T star, right? Let's say X bar plus minus T star times S over root N. If this is negative, right, then the plus becomes a subtraction and the minus becomes addition. And so it just kind of flip-flops between the two. As long as you list them, the answers from lower to upper, then you're fine, right? Just kind of keeping track, because the value is going to be the same. It's just whether it's kind of adding or subtracting first, effectively. So, nice. You bet. And my other 2 classes had a test last week. So of course I posted part 1, implying there's going to be a part 2 last week. Well, I completely forgot. So I'll just, there's just a part 1. Don't worry about that. I'll just do it this week. We'll do 2 samples. But just for a little bit of review, I hate that I don't have lines on here, but I can't figure out how to do them when I'm sharing my screen, so, oh well. Last day we talked about t-tests, which we use for a number of different things, right? We could have one sample mean, like the assignment that we wanted, that you were working on. So one sample mean compared to some mu naught, some value mu naught. That's a t. We could have two samples. And those two samples of numerical data, I'll add, right? Because t-tests are for numerical data. So we could have two samples of numerical data. And we said, well, there's actually two ways that we could have two samples of numerical data. We could have them paired on each other, right? So two observations on one subject, right? Kind of a pre-post score. If you want to capture maybe day-to-day variation, right? And you've taken measurements on the same day, then you could pair them on the same day. And so here we have paired data, which is when we have two observations on the same subject. Kind of pre-post scores, right? Kind of before and after some treatment, right? Then we go back and measure it, or kind of day-to-day variability, right? So we could match on the day or match on the day, right? Traffic on Monday is different from traffic on a Saturday, right? So for example, traffic on Monday is different than Saturday. Oops. Or if we have two independent samples, then we treat the two independent samples as just two groups, right? And so now I have a mean and a standard deviation and a sample size for each group. Whereas you might remember for paired data, what was the trick that we used? We calculated the differences, right, in each of the pairs, and then we analyzed the one sample of differences, right? And so here, calculate the differences, and then analyze one sample of differences. So then it's back to one sample mean, right? But you have X bar of the differences, you have S of the differences, you have some number of differences, and you want to compare it to mu equal to 0. In fact, you want to know if mu diff is equal to 0. And that's your null hypothesis. So we want to know how far is that average difference from 0. Whereas if we have two independent samples, right, then we just want to compare those two means to each other. Now, this is probably the most common t-test that we do, is comparing two independent sample means. And so we want to compare mu1 with mu2, right? The population mean of group 1 with the population mean of group 2. And so our null hypothesis is going to be that mu1 minus mu2 is equal to 0. Right? This is the difference in the means as opposed to the mean of the differences. Right? And so I like to write it like this instead, mu1 equals mu2. Right? I can add mu2 to both sides. And then I can say, okay, well, what I'm actually hypothesizing about is whether these two means are equal to each other, or usually what I want to show is that they're not equal to each other, or one's less than the other, or something like that. And so then we have x1 bar, s1, n1, x2 bar, s2, n2. And our formula was quite a bit bigger, right? And so t is x1 bar minus x2 bar. Technically, I'll throw it down here. Technically, we're seeing how far is this point estimate of the differences in the means from our hypothesized difference in the point estimates, which is from up here. So this 0 comes from here. But we don't really write that usually. And then the standard error is quite large just because we have all the standard deviations and sample sizes. And so the square root of s1 squared over n1 plus s2 squared over n2. There is a t.test function. So in Excel, there's a t.test function which takes sample 1, sample 2, sample 1, sample 2. They call it array 1 and array 2, I think, but makes more sense to think of them as samples. And the next thing it takes is the one-sided or two-sided, one or two-sided test. One-sided meaning if you want to know if one's less than the other, right? You're only concerned about one extreme. Or two-sided if you want to know if the mean difference or the difference in the means is significantly different from 0. And then this last part is the type. And I want to talk about the type because I know last day I just said, explore this function and try it out. And so the type, there are 3 options. You can tell it that these 2 samples that you've given it are paired, right? Then it treats them as paired data. The second type is independent, equal variances assumed. We're going to use this one. We can assume equal variances for almost all that we do. There are tests. What would you have to do? You could see if the variance of group 1 is significantly different from the variance of group 2, and there are hypothesis tests that we could run to test it, but for us, we're just going to assume equal variances. Okay, and so that can be confusing, right? If you're trying to read up on it, and how do I know? And so for us, just simplify things and just assume equal variances. The other option is, of course, 2 independent samples, non-equal variances or something like that. They might talk about homoscedasticity. Let's see if I can spell that. skedasticity. I feel like this could be a K. Maybe. And then heteroskedastic. Homo means one. Skedasticity is the variances. I feel like it is a K. Just gonna go for it. But for us, if you have, so you're choosing just between 1 and 2, whether you have paired data or independent samples, then it'll calculate your T for you and return the p-value, right? Whether it's the one-sided or the two-sided p-value depends on what you told it that you want it. So it'll do the work for you. But the hard part is figuring out what type of test you want to run, right? And so you really only need this T if you only have the summary information, right? And so of course, this T.test requires the actual samples. Okay. So here requires raw data. Whereas a lot of questions will just give you the summary information. So then you would have to use the T function, the T calculation. What's the T over here, just for completeness sake? T is X bar diff. How far is it from 0? Oh. Oh, weird. That's weird. I don't have like a waiting room or anything. Yeah, there's people in here. I'm not alone. Oh, that's weird. Huh. Yeah. Oh, that's quite all right. Yeah, that's weird. I wouldn't. Is he going through Moodle?
He must be. He's
Yeah.
a smart guy, I'm sure if it's.
Okay. Yeah, weird. Well, I'd be worried if I was alone in here, but I'm not. So then I'm kind of. Yeah. Or mine. I'm open to that. Oh yeah, here, S diff over the square root of N diff, which means that you would need to have the summary information for the differences. Okay. And so if you have raw data, then I would just go for the T.test function, but it is a little finicky because it requires 2 samples. So for some reason, they don't do it for 1 sample, and you need to figure out what type you have. Okay. The last thing that I want to just touch on is, what if we have 3 or more means that we want to compare, right? So we did that for proportions, right? We went from 1 sample proportions to 2 sample proportions. What if I want to compare the 2? And then, well, what if I have 3 or more proportions? Then I have a chi-squared, right? And what if I have 2 categorical variables? Then I have a chi-squared again, but a test of independence. And so if we have, or if we want to compare 3+ means, the test that we use is called an ANOVA. We use an ANOVA, which is an analysis of variance, which I remember thinking, oh, that's so weird, because what, we're going to use an analysis of variance to test the means? And it is weird. It's the background that it uses, is the theory that it uses to test the means. But for us, what we want to know is if there's anything going on. And so the ANOVA has a look, I kind of think of it as a box. You've got 3 or more means that you want to know, hey, is one of you different from the others? And the ANOVA will just say yes or no. It's not going to tell you which one, but it will tell you if anything's going on. That would be valuable, right? Especially before computers, because what would you have to do? You'd have to do pairwise comparisons to figure out which one is different, right? And so if you have a tool that is easy, relatively easy to calculate, right? That tells you, hey, is there anything worth pursuing in here? Yes or no, right? And so that's what the analysis of variance does, or the ANOVA. The ANOVA only tells us if there is a mean significantly different from any of the other means. There could be 2 that are significantly different from each other, or there could be, they're all different from each other. And so, but all it does is it tells us if there's a mean significantly different from any of the other means. It does not tell us which mean is significantly different. I want to go back up here and maybe I'll put it. Put it up down here. Hey, I'm just trying to move it. It's not a huge ask. Okay. I can't remember if I showed you guys this. I feel like I have. Yeah.
Oh, yeah.
It's my go-to.
Yeah.
It's like, so I have it. I have it on the tree just as a little reminder. So we've talked about lots of different types of questions, right? And so I just want to give you kind of a quick summary, and I'll post the Word document for this as well. It was a pain to do in Word. I don't use Word that often, but man, is it annoying. Can use LaTeX instead. But to type this up would take forever. So first thing that you want to do is just identify what type of question you have. And so the first decision that you're going to make is, do you have a proportion question, right? So do you have categorical data? Oops. Or do you have numerical data? Oops. Right. And so that's why it's so important to, in the beginning, spend time figuring out, okay, is this a categorical variable or is this a numerical variable, right? And depending on what test you want to run, there are sometimes variables where you kind of get to choose, right? Do you want to have income categories or just raw incomes, right? And then that would set you on two different paths depending on what you choose. So then we started over here with proportions, right? So for categorical data, we analyze the proportions, and we can have a one sample proportion. We can do a hypothesis test or a confidence interval. And depending on the hypothesis test or the confidence interval, these are the conditions. We didn't spend a ton of time here, but so this layer are the conditions that have to be satisfied. And so randomly sampled, and we have to have at least 10 expected successes and failures. And we kind of glossed over that because we said, well, everything's just going to have to be satisfied anyways before we go ahead and do this. In terms of the formulas, now this is from a different course, so we didn't do a sample size calculation, but we could have. But we've got your null and alternative hypotheses and your Z calculation, and then you use Excel to find the probability, the p-value. If you have two samples of categorical data, you're likely going to want to compare the two proportions to each other, right? Probably do a hypothesis test like this. And so P1 is equal to P2, or if you prefer, P1 minus P2 is equal to 0, right? That's the same. It uses the pooled proportion, right? Down here, this is just another version of this first calculation, right? And so it uses the pooled proportion. If we have 3 or more categories, right, then it's going to be a chi-squared. And we talked about 2 different chi-squared tests. So if I have one variable, then I want to test it against some expected distribution, right? And then I briefly introduce the 2 variables, the test of independence, and depending on which one, right, still a chi-squared test, which you calculate the same way, but your expected values come from different sources, right? So in the chi-squared goodness of fit, then you have your expected value from the expected distribution. Whereas if you have a test of independence, then you use the row total times the column total divided by the grand total. We also explored the chi-squared test function in Excel, and it gives you the p-value immediately. So that's kind of nice. From 3+ categories, there's nowhere else to go. So that's nice. We've kind of tapped out. If we have numerical data, then we're analyzing the mean, right, or the average. If I have one sample, right, then this is where you were working last week, right? Then we have NX bar. It follows a t distribution with n-1 degrees of freedom. And the standard error is S over root n. If you have 2 samples, 2 numerical samples, this is where we were kind of reviewing, then the first option is you have paired data. The second option is you have 2 independent samples. And if I just skim down to the formulas, right, they're quite different. This, besides the diffs, all the diffs on here, this is the same as a 1 sample t-test, right? Whereas here, all these formulas, right, take into account the information from the 2 independent groups. There was no way to combine them anymore, and that's okay. And then here, just briefly, I introduced, okay, well, what if I have 3+ groups? Then we do an ANOVA, an analysis of variance. And if we're comparing many means with ANOVA, then your null hypothesis is that each of the means are not significantly different from each other. They're all the same, right? And so that's why I think of it as a box. Hey, anyone different in there? And it just says yes or no, right? The alternative hypothesis is that at least one mean is not the same or is significantly different from another mean. So at least one of them, where of course we're not talking about the same group. Okay? We don't need to worry about this table, okay? But we do need to worry about this test statistic. Okay? The test statistic that we use is called an F statistic. Of course, Excel is going to generate this table, and F, just like chi-squared, is a skewed distribution, and it depends on two sets of degrees of freedom, right? So it has degrees of freedom 1 and degrees of freedom 2. Now, if you give Excel the data, I feel like it'll just know what the degrees of freedom are because it generates this table. So we don't need to worry about it too much. But here, up to mu k tells me that I have k groups that I want to analyze. Okay. And so we're going to have some degrees of freedom between the groups, and that degrees of freedom is k minus 1, so the number of groups minus 1. And then we're going to have degrees of freedom for the residuals, which is going to be n minus k. There's also a total down here, but I didn't include it. Okay. But because I suspect that you won't need to do an ANOVA too often, you can consider it. But I can't really think of when you guys would do an ANOVA in your comparing 3 or more means. Maybe 3 or more streams. But then you might have kind of something more precise in mind anyways, right? And so, and the reason I'm skimming it is because there's a lot of theory here and I want to skip it. I will post the video though, but I'll make it a bonus assignment. So if you want to boost your assignment grade, then you can do it. If not, it'll just get dropped. So Moodle will be set to drop your lowest assignment grade. So if you don't do it, that's totally fine. But just to explore the ANOVA, there'll be a video and then can work through it. What did I want to do today? Only took me a little while to get there. Today, I want to start, and I would love. Okay, you know what? I need some lines on here. I'm just gonna briefly stop sharing my screen because I feel like that's why. No, it's not. Okay. Share my screen. Start. Oh, there's a chat here. Oh, awesome. You made it in. Nice. Welcome. Let's see here. I need to discuss this to be able to add lines. Seems like a simple ask. But no. Lines. Yay. Okay. So as far as inference goes, hypothesis testing, confidence intervals for all those different types of questions, we'll kind of parking lot that a little bit. And I want to turn our attention to what's called regression. Regression is essentially fitting a line of best fit, fitting a line or a line of best fit. So we'll just start by reviewing some of those core concepts, such as, well, if I am fitting a line, you've probably in your mind imagined a scatter plot, right? So you've got some variable on the x-axis and some variable on the y-axis. Right? And then you've got your ordered pairs from your data that you've collected. Maybe something like that, right? So each observation has an X and a Y observation. Okay. So I remember, I think it was like chemistry 11 or 12 or something, and we had drawn our scatter plot, which is crazy, by hand. And then we were told, oh, okay, just use a ruler and fit a line of best fit. And well, what did we do? We just kind of drew a line. Cool. There's a little bit more to it. Obviously, there's math involved. But Excel just does it for us, so we're not going to concern ourselves too much with the math. But I want to talk about some core concepts here today. So if we take a step back and think about, well, what was my mind doing when I was drawing this line of best fit, right? We're not wrong. It's just there are formulas that we can use. And so if we had to articulate it, I'm trying to minimize the distances between the points and the line that I draw, right? That's what makes a line of best fit. And so here, the line should minimize the distances between the points and the line. That's what makes a line of best fit. That's hard to put your finger on, right? But then when you hear it, you go, oh yeah, of course. That makes sense, hopefully. One really neat thing is a lot of data is linear like this, so we can fit it or we can model it with a straight line. Now, in general, you might remember y equals mx plus b as an equation of a line, right? Where m is the slope and b is the intercept. It's the y-intercept, but I never call it the y-intercept. I just call it the intercept because we never care about the x-intercept. So, I'll call it the intercept, right? But so we know the equation or the general equation of a line. The slope is rise over run, and the y-intercept is where it crosses the y-axis, right? This line. So there are a lot of things that we know already, right? But why would we want to use this model, right? One of the main goals of regression, and remember, I'm just using regression as shorthand for fitting a line of best fit, right? So one of the main goals of regression is to predict values of y. And one of the problems is the same as for inference. Well, this is just based off of a sample. right? And so I've taken a sample of, I don't know, I guess we could talk about water samples, right? And so I've got a series of water samples. I have two measurements. The explanatory variable, just as a little refresher, the explanatory variable goes on the x-axis. You could also call it the independent variable. But I like explanatory because then it's more obvious which axis it goes on. And then we have the response variable or the dependent variable. Oops. On the y-axis. The response variable is the thing you want to predict, right? Or the variable of interest. We want to predict this. A lot of the time, you'll have a small sample or some smallish data set on two variables, right? The thing that you're interested in, the y, and then something that you hope explains changes in y, which is the explanatory variable. Okay, and one of the main things that we do use this for is if y is expensive to measure, right? But we think that we could use a different variable that's inexpensive to measure to predict values of y, then that's really valuable, right? And so what can we do? Well, when we live in a shoe, y hat is what we're going to use to denote that this is my predicted value of y. So y hat is the predicted value of y. We've seen hats before, but that was in the proportion case where it was denoting that, hey, p hat is a sample proportion. Context will tell you that this y hat is the predicted value of y. And so never the two shall meet. And so context will tell you what the hat means, whether it's a sample proportion or a predicted value of y. But we're going to use y hat. Now, like we were saying, this is just sample information, right? And we're hoping that it represents a mini version of the population, right? And so that's what we're going to use to make predictions, right? And so for the population, technically, you would have y hat beta naught is beta naught plus beta 1 times x. Okay. Greek letter beta. Beta is spelled beta because it's the population. So we use Greek letters. We'll never know what these values are, but we are trying to learn about what the population behavior is, right? And so same as before, right? Whatever is attached to the x is the slope, and whatever is on its own is the intercept. It's the same as y equals mx plus b, except it's y equals b plus mx, but just doesn't have that same ring to it. Right. For our sample, our model is going to look like this. B0 is the point estimate of beta naught. So B naught is the point estimate of beta naught, and B1 is going to be the point estimate of beta 1. point estimates. These point estimates have standard errors, but they'll just be generated through the output. And so we don't need to worry about that. Okay? For us, just trying to establish what we're doing here today. Okay. Like I was saying, a lot of relationships are linear, but I know that you guys work on a log scale a lot of the time, right? And so because you've got exponential measurements or kind of whatever you're working with, right? And so what you're doing when you're working with that log scale is you're doing a transformation, right? And then you make it linear, right? And so even if you have non-linear data, a go-to move is to transform either the X and or the Y until you have a linear relationship. It makes the interpretation a little bit difficult, right? Because then you have to untransform it. Okay? And so even if a relationship is not linear, right? Linear meaning straight line. Okay. So if you can't model it with a straight line, we can transform Y and or X. Often we do both, right? You guys work on a log. Is it log paper? Log paper? Allison was showing me this crazy graph paper that she uses. And it's already done the log transformation for you. And it's all kind of like smushed, and then spread out. It's kind of this weird paper that she showed me. I'll have to dig it up. But Excel can just do that for you if you just take the log of X or Y or both. We often start by considering the log. For where I come from, I use the natural log. In fact, when I teach pre-calculus or whatever, I throw off my students because this is the only log for me, the natural log base E. And so I just call it the log, which is very confusing because typically the log is log base 10. But log base E is my go-to, right? And can play around with them, but usually log base E is the better one for us. Log base 10 is more for kind of sound waves and stuff like that, and so more electrical engineering. But I don't remember what Allison said, if she uses 10 or E. Something to look into for me. So what can you do? Then you can have the log of Y, right? The predicted value of the log of Y is equal to beta naught or B naught plus B1 X maybe, or the log of X. That looks tricky, right? But all you're doing in your Excel spreadsheet is you're generating new columns where you've taken the log, whatever base you want, of X and Y, and then using those in your scatter plot. Right? So we can use transformations, and there are other transformations, but a lot of kind of natural data is exponential, so then you can make it linear by taking the log. Okay. So what am I doing? Okay. Or where am I, rather? Let's just assume that we have a linear relationship. Okay. We talk about the correlation a lot. Just we use the term in just regular speech, but really what the correlation does, the correlation is a numerical measure of the strength and the direction of a linear relationship. And so the correlation is a numerical measure of the strength, right? Which is really just how close are the points to the line, right? The closer they are to the line, the stronger they are. And so it's a numerical measure how close points are to the line. And direction, right? Either it's positive, which means it's going up like this, or negative, which means it's going down like this. So as x is increasing, y is decreasing. Or if it's positive, if x is increasing, y is increasing. Of a linear relationship. Has to be of a linear relationship. So going back to the normal distribution, right? We said, okay, if I have a histogram and I'm looking at the distribution, and then depending on the shape, that will determine what the appropriate center and spread are, right? So we said if I have a normal distribution, then I can use the mean and the standard deviation as the numerical measures of center and spread. If I don't have a normal distribution, then I should be using the median and the interquartile range. And so the problem is Excel will just calculate whatever you tell it to, right? And so even if you have a non-normal distribution, you can still find the mean and the standard deviation. They're just not very useful, right? And so same thing with the correlation. And so we can always calculate the correlation. And of course, we're just making Excel do it. So we can always calculate the correlation between two variables. I'll say two numerical variables. But it's only appropriate if we have a linear relationship. But it is only appropriate if we have a linear relationship. So that's important. Now correlation is denoted by R. Lowercase r or capital R, depending on what textbook you're reading. I use lowercase just because that's how I was raised, academically raised. And it's the most common version, but I have seen capital R, but I just can't get there. And so R, the correlation R is between -1 and +1. -1 is a perfectly negative relationship, and +1 is a perfectly positive relationship. Okay? And if R is 0, there is no relationship. So I like to think of the correlation as being on this kind of scale from -1 to 1 with 0 in the middle. The correlation is a numerical measure of the strength, right? And so the closer we are to 1 or -1, then we have a strong relationship. And the closer we get to 0, the weaker the relationship is. But it also tells us the direction just by positive or negative. And so here we have a positive, or sorry, that'll throw you for a loop, a negative relationship between X and Y. And here we have a positive relationship. Let's see. So at -1, what the relationship would look like is something like this. They're all exactly on the same line, and you can capture them all. Should make these bigger. With the same line. That's one, not very interesting to model, and two, never really going to happen unless you have some sort of machine that if you just let it run for longer, it'll just keep producing whatever it's producing, right? Then that's a perfectly linear relationship, but we don't tend to model that. And so on the flip side over here, we have the exact same scenario, just moving in the positive direction. A relationship of 0, or a correlation of 0, I should say, is going to look like this, right? So now it doesn't matter where you draw your line, right? It may as well just be straight across. You could draw a line like this, but it won't let you. You could draw a line like this or something in between, but really, I'll delete those because here, this is going to be the line that models this relationship. Why? Because the slope here is 0. The slope is 0, which means that there's no relationship. No relationship. Why can we say that? Because I could plug in this value of X, and remember the line gives me the predicted value of Y. So I would get this predicted value of Y, and I could put in a very large value of X, and I would get the same predicted value of Y, right? And so each or every value of X generates the same predicted value. And that's where the no relationship comes in, right? And it's because the slope of this line of best fit is 0. So every value of X generates the same Y hat. Right. That's not useful to us. Whereas over here, right, here I have a value of X that's small, and so I get a small predicted value. Here I have a value of X that's larger, and so I get a much larger predicted value of Y, right? And so that's useful to us. And most of the time we have something in between, right? Maybe we have some line like this, and we just kind of have it go like this. right, we've got scatter all around. So we said that the correlation tells me whether it's a positive or a negative relationship just by the value, right? But then also the strength of the relationship. And for me, I like to use kind of negative 0.5 to 0.5 as my cutoff. Okay? Just rough approximations. So if you get a correlation between negative 0.5 and 0.5, I would call it weak. Whereas anything after 0.5, then you're going to start to see a pattern, and then I would call it strong. We can have a strong positive relationship, or we can have a strong negative relationship. And you can throw kind of descriptors on there like moderately strong, moderately weak, right? But I'll just stick to weak or strong, even though you're welcome to embellish a little bit. If you see a pattern, right, on a scatter plot, then it's going to be a strong relationship, right? It could be, if it's hard to see the pattern, then maybe the correlation is going to be close to 0.5. But a correlation of 0.5, it's really hard to see a pattern. And so that's why I use it as an approximate cutoff. But just as a rule of thumb, if you can see a pattern in the scatter plot, the relationship is strong, or moderately strong is if it's kind of hard to see. So just as a gauge, right? If you're looking at a scatter plot and you see a pattern, then it's going to be strong and it's worth modeling. Right? If a relationship is weak, right, that's not worth modeling, right? We could still, just because in the nature of your data collection, right, you might have weak relationships and you still want to model them, but usually we don't pursue it, right? We might just try it and say, oh, there was a weak relationship, and so then we don't use it to make predictions. And so if a relationship is weak, we usually don't use the model to make predictions. You guys used R squared before. If I say R squared, it's ringing a bell. Probably, maybe. I know, we just use it blindly. And it is a good measure. It's a goodness of fit measure. And so in regression, when you fit a line, and hopefully you've fit a line, you right click on a dot in your scatter plot and say add trend line, and then it adds the equation of the line. And so that's nice. So it's not hard. We're not going to talk about the equations or anything that go into it. We just need to be able to do it. But for us, what I want to focus on today is just figuring out what the R squared is. And so R squared, totally, right? And so, and that's all we know. And that's really all you need to know. It's my job to tell you what it is, and then, oh, okay, that makes sense. But it's, so R squared, but yeah, in the applied world, that's really all you need to know. It only really applies to linear models, right? And so R squared is a goodness of fit measure, right? How well does the model fit your data? How well does the model fit the data? Right, that's what we want to know. R squared is the correlation squared. The correlation squared. That's neat, right? The correlation goes from -1 to +1, right? Up here, -1 to +1. But if I square a negative value, it becomes positive. So then all of a sudden I'm on a 0 to 1 scale, right? And so that's why it's a percentage. And so R squared, how do I? Since R is between -1 and 1, R squared is going to be between 0 and 1. I'll space these out so they don't look. Right, if I square a value that's negative, then it becomes positive, but the maximum value 1 squared or -1 squared is going to be 1. And so this makes it, this is a percentage. It's a proportion, right, between 0 and 1. So maybe I should be proper. This is a proportion which can be converted to a percentage. So the R squared then, right? The reason you want a high R squared is because, okay, then how do I get a high R squared? Well, I get a high R squared by having a correlation closer to 1, right? So a high correlation, which means that my line is going to capture a lot of the activity. And so R squared is the percentage of variability in Y, oops, explained by the least squares regression line, which is the method that we use most commonly, and that's the method that Excel uses, the least squares regression line. On X. That's the definition of R squared. Okay? And so if you have a Y variable, right, then you would sub in the Y variable. And for this reason, so it's the percentage of variability. So the percentage of activity in Y that's explained by this model, right? And so that's why a high R squared says that this model is doing a good job of predicting Y. And so here, therefore, a high R squared means the model does a good job of predicting Y. Whoops, disappeared. There. And so that's why you want a high R squared, because it does a good job of predicting the Y variable. Okay, nice. Close enough. Not gonna start anything. If you have any questions, let me know. Otherwise, I guess I'll see you on Monday. Oh my gosh. Oh my gosh. It's crazy.